Hey guys, so today I have a sort of a calculus 3 type question. It could also be used in physics. It's basically an application of calculus and it's physics. The topic today is projectile motion. The question is, if a projectile is thrown into the air with an original angle of elevation, let's call it theta, show that it reaches 3/4 of its maximum height at half the time required for it to fully reach its maximum height. So let me explain the scenario to you. So you have some object, let's call it a soccer ball or anything like that. And mass is irrelevant in a projectile motion. It has an original angle of elevation, which means angle to the ground of theta, which looks something like that. And your object, this straight line here is the ground, and your object here, this is your projectile. Let's say this diagram is not drawn to scale, obviously. If this is the maximum height at time t, then t, and then it has a height of h, show that at time t equals 2, at t over 2, it has 3/4 of its maximum height, which is h. So how do we do that? Well, to do that, thinking of this from a physics perspective, this also works when you're considering calculus 3. Let's break this initial velocity up into its components, x and y. X represents the horizontal direction and y represents the vertical direction, okay? So your v naught is your initial velocity. Initial velocity, right? Okay, now x is equal to now what do you know about, like, let me just write this down. So it's like x is v naught cos theta t, because motion is constant in the horizontal direction. You only have one force, and that's gravity, and gravity is always downwards, direction downwards, and it's a constant negative 9.8 meters per second squared. That's the only other outer force. We're ignoring air resistance here. Outer force. No air resistance. I technically know how to do this with air resistance. I learned it when I took ordinary differential equations. You basically involve some sort of drag coefficient, which is approximately proportional to the mass of the object, but we're not doing air resistance here in this calculation. And that's like one of the simpler cases. The air resistance can get really messy. It's negligible in many cases. All right, so that's your x. So it's v naught cos theta times t, constant motion without any acceleration horizontally. The vertical case is a little different. Y is equal to, okay, so v naught sine theta t minus 4.9 t squared. And let me explain this equation first of all. So usually, like, here's the equation that's like, that you'll probably see in physics. D equals v naught t plus 1/2 a t squared. T in this case, the time it takes to reach the maximum height. And v naught, I wrote v naught sine theta because that's the vertical component of the initial velocity. And we have to have this plus 1/2 at squared since gravity is a constant downwards negative 9.8 meters per second squared. Now, yeah, so 1.2 times negative 9.8, that's negative 4.9 t squared. All right, so now we have our components of the projectile motion. And like I said, V naught is the initial velocity. Since we're considering the maximum height, we can say y prime of t, I'm taking the derivative of this, is equal to V naught sine theta minus 9.8 t. Okay, and at the maximum height, y prime is 0. So when you move this equation around a bit, you get t is equal to V naught sine theta over 9.8. And remember, this t is the max time it takes for the object to reach its maximum height. Now, considering the considering back to the y, like substituting back this into the original equation y, we have y is equal to, and just substitute this t value, and you get y is equal to V naught squared sine squared theta. V naught squared sine squared theta over 9.8 minus 4.9. I'm just plugging this into this equation right here. 4.9 V naught squared sine squared theta over 9.8 squared. Okay, and this is equal to, when you should simplify this, and when you do simplify it, it simplifies to 1 over 19.6 V naught squared sine squared theta. All right, and this is your maximum height. Max height h. All right, now let's consider what happens when the ball is like at half the time, at t over 2. So at t over 2, so this is the time it takes for the ball to reach its maximum height. So we say here at t is equal to V naught sine theta over 19.6, because that's half the time. Sine theta over 19.6. What happens here? Well, you can plug this value into your y here, and what you get is y is plugging this into this t here for y. Y is equal to V naught squared sine squared theta over 19.6 minus 4.9 V naught squared sine squared theta over 19.6 squared. And when you simplify this out, you get, I don't want to sound pretentious, so I'm gonna like do this slowly. So let's do some math over here. V naught squared sine squared theta over 19.6. V naught squared sine squared theta over 19.6. So let me do this. So it's like 1, you can factor out a 1 here. And here you can factor out a 4.9 over 19.6. But that's just 1/4, so you get 3/4 of this term. So that this y is equal to 3 over 4 1 over 19.6 V naught squared sine squared theta. All right. And this is what we want, because we know our maximum height is 1 over 19.6 v naught squared sine squared theta. And when t is equal to half the t here, our height is 3/4 of this maximum height. So therefore, we're done. We have answered the question. We have shown that when the ball reaches 3/4 of its maximum height, it's at half the time required for it to fully reach its maximum height. So that's all for this video. Thank you guys very much for watching. I'd love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.